Hello guys, today I'll be explaining the topic 1 experimental techniques. You can find it on SDP. It's 25 pages long, so this video might be long, I'm not sure. Okay, but so far it seems really easy, so let's start. First of all, we have the particulate nature of matter, the states of matter. We have 3 states, which are solid, liquid, and gas. They told us that all matter is made of tiny particles. These tiny particles, we call them atoms, or in chemistry, they refer to them as particles. They are way too tiny to be seen by the naked eye. You can look at them through an electron microscope, okay? So, in the 3 different states of matter, okay, the particles are made in they are arranged in a different way and they move all in a different way. And of course, by changing the amount of energy, by adding heat or removing heat, okay, by giving more energy or taking away energy, we can change the state of matter. So they gave us a table over here. Okay, I don't think the table fits. Actually, it does. Okay. And they're going to explain to us each state of matter, how it works. So we first start off with particles in a substance. We're going to start with a solid. In the solid, we have what? You see that the particles are so tightly compact, okay? They vibrate with respect to each other. Then we're gonna move to the liquid. In the liquid, you see they are not as compact, they're not as close, okay? But they can move with respect to one another. And finally, in the gas, you will see that the particles are very far apart, they're not close together, so this gives them a lot of space to move. Now, talking about the space between the particles, of course, solid are very close and compact together. They're touching one another. Liquids are the same thing, but you can say they move with respect to each other. Here they vibrate with respect to each other, and here they're very far apart. So they're far apart. They're just gonna move. Okay. Now the arrangement of particles. This is a very important concept. In a solid, the particles are regular repeating patterns, meaning they do not change easily, okay? So, for example, a tissue box, if you put it in a different container, will it change its shape? No, if I put it on my desk or if I put it on my floor, it's the same shape and the same size. So we say it is a solid because it has a regular repeating pattern. However, a liquid, for example, we have water in the bottle and water in a glass cup. You put water in the bottle, for example. Will it visibly, is it the same? Does it look the same as if we put it in the cup? Definitely not. So that's why we say it is irregular arrangement of particles, because they can change the shape of the liquid. You can only change the shape of the liquid and you cannot change its size though, okay? Only the shape. Now, however, for gas, okay, gas is a very different state. You can change both its shape and its size. Okay, so think of it like this: arrangement of particles of solid, shape and size does not change. Liquid, shape can change, size cannot change. Gas, shape and size can change. Now, the movement of particles, which we discussed earlier, we know that solids vibrate around their fixed position but do not move apart. We also know liquids move around and slide past each other. And then finally, in the gas, they move freely and collide with each other, meaning they hit each other. Now we come to a nice topic, which is the forces between particles. The forces are kind of like the bonds that keep them together, okay? Definitely, the solids have the strongest bonds, okay? So they have bonds stronger than liquid. Liquid have bonds, but not as strong as solids. And then finally, in gas, you don't have any bonds between the particles, because they're just moving freely, they're just existing. Then, now for the shape, here we have a fixed shape, like we said, the tissue box example. Then for the liquid, it takes the shape of its container, and the very same thing goes for the solid. However, when we're talking about compression, okay, you should know that solids and liquids cannot be compressed. The only element that can be compressed is gas. Sorry, not the only element, the only state that can be compressed is gas. Okay, so this was like a quick brief summary about the 3 states of matter. So now we move to what? We move to the changes of state. Okay, we're gonna explain each one by itself. Also, I apologize for my voice change. I'm a little bit sick, but it's okay, okay? So, when we're going from solid to liquid, we have two ways actually. From going to solid to liquid, this is called melting. Or going from liquid to solid, this is called freezing or solidification. So very simply, like that, we finished what? We finished the liquid and solid. Now, if we're talking about liquid and gas, if we're moving from liquid to gas, this is boiling or evaporation. And if we're moving from gas to liquid, this is condensation. Now, finally, we have what? We have gas and solid. If we're moving from solid to gas, it is sublimation. How I memorize it personally is that as solid as sublimation. Okay, so you start with a solid, it's sublimation. Then finally, from gas to solid, it is called deposition. So that is it for the changes of state. Then they're gonna do a description for each of the changes of state. Melting is the change from solid to liquid at a definite temperature. Okay? This is an endothermic process. Endothermic means that it requires energy, it takes in heat. Okay? Boiling or evaporating is from liquid to gas at a definite temperature. Again, it's endothermic, so it's taking in heat. It's taking in energy. Then we have freezing or solidification. It is the change of state from liquid to solid at a definite temperature. Now the difference is that it's exothermic. Exothermic means it's releasing heat, it's giving away energy, okay? Condensation is from gas to liquid at a definite temperature, and again, it is what? It is exothermic, meaning that it releases heat, it releases energy. Finally, we get to sublimation. Now, this is very important. The change of state from solid to gas without passing through the liquid state. An example includes solid carbon dioxide, iodine, and ammonium chloride. Here, they're telling us that this process is exothermic. Exothermic means what? It means that it releases heat, it releases energy. So this is it for the changes of state. Now, we are gonna go to what? We're gonna go to something called kinetic theory of matter. Basically, three main things you should know about the kinetic theory of matter. Matter is made of tiny particles that are always moving. The less the weight or the less the mass of the particle, the faster it moves, and if you increase the temperature, the particles move faster. How they stated it is that matter is made up of tiny, invisible meaning you can't see it with your eye, particles that are in constant motion. The lighter the particle, the faster it moves, and then as the temperature increases, the particles move faster. Now we have something called Brownian motion. Okay? Brownian motion states that particles in fluids, both liquids and gases, fluids means liquids and gases, move randomly. Now this random motion is called the Brownian motion. Now, you may be asking, why do they move randomly? Don't also the particles in solids move? Yes, they move, but in fluids, which are liquids and gases, they bombard each other, they hit each other, so they are bombarded by the other moving particles in the fluid. So, again, larger particles can be moved by light, fast-moving molecules. That means big particles, if you shoot something small, even that's moving really fast, okay, it can make these particles move. Now, Brownian motion is named after a scientist called Robert Brown. What did the scientist Robert Brown do? He first observed this motion, this Brownian motion, okay, where the particles in fluids move randomly in 1827. He used a microscope to look at pollen grains moving randomly in water. At this point, he could not explain why this occurred. So he saw this random movement and he didn't understand why this happened. So he couldn't explain it. But then, a couple of years later, in 1905, Albert Einstein, which I believe everyone knows him, he was a physicist, okay? He explained that the pollen grains or being moved by individual water molecules, meaning that the water molecules are atoms, okay, and the pollen grains are moving because of the motion of the atoms of water, okay? So when Albert Einstein said this confirmed that atoms and molecules did exist, and so thanks to Robert Brown and Albert Einstein, they made an evidence for the particle theory in that that there are atoms. So now, diffusion. Diffusion is the continuous movement of particles from one place to another to fill the space available for them. Diffusion occurs in both liquids and gases. Basically, diffusion is when, for example, you have two objects. Let's say you have water and you have colored water, okay? When you add the colored water into the water, it will spread out and then all the water will become colored. Why? This is because of something called diffusion, where it's the continuous movement of the particles. In this case, the continuous movement of the colored particles from one place to another to fill the space available for them. So now they're going to explain to us diffusion in gases. They told us in example 1, they used bromine or nitrogen dioxide. So what exactly did they do here? They said 2 gas jars are placed on top of each other separated by a glass cover. So this is jar number 1, jar number 2, separated by a glass cover over here. Then they proceed to tell us that the top jar contains air, so over here we have air. The bottom jar contains a gas denser than air, so heavier than air, which is, for example, bromine vapor or nitrogen gas. Why do they use it? Because they are colored, so you can see them. So they're telling us if the glass cover is removed. So if you remove this cover over here, what happens? The colorless air moves down and the colored brown gas moves up. So the air will move down and the gas will move up. And so they will mix together to form one thing, one color or one gas. This is clear evidence of diffusion due to the random continuous movement of all the gas particles. So they continue moving until they become constant or one visible thing. Initially, the net movement of one type of particle is from a region of higher concentration to a region of lower concentration. Meaning here we have a high concentration of air, a low concentration, let's say, of bromine, okay? But then down here we have what? We have a higher concentration of bromine and a lower concentration of air. So usually it moves from the higher concentration to the lower concentration. So let's say green is for air. The air will move like this. Let's say red is for bromine. The bromine will move like this. So the bromine will move from the bottom to the top because the top has less bromine. So it's moving from the higher concentration to the lower concentration. Then the air will move from the top to the bottom because the bottom has less air. So it's moving from the higher concentration to the lower concentration. When fully mixed, no further color changes. The distribution is observed. So as we said, the visible changes can no longer be observed. Okay? But pay attention, the random particle movement continues. So they are still moving, even though they mixed and they finished mixing, they are still moving. Okay? Now they're gonna use another example. Example 2, the formation of aluminum chloride. So let's see what they did. Here they used what? A pad soaked in ammonia solution. Okay, so here we have ammonia solution. Then over here we have a white ring of ammonium chloride. So they put a barrier, which is the white ring of ammonium chloride. Then they put another pad soaked in hydrogen chloride solution. Now, why did we use ammonia and hydrogen chloride? They said because ammonia and hydrogen chloride react to form a white solid, which is ammonium chloride. So actually now this is not the barrier, this is the white solid. So they explained it like this: NH3 gas plus HCl gives us NH4Cl solid. So this moves here and this also moves here, so they combine to form this over here. Now they're telling us a piece of cotton wool soaked in concentrated, not dilute, concentrated ammonia solution, a source of ammonia gas, is placed at the end of a long glass tube. Okay, a piece of cotton wool soaked in concentrated hydrochloric acid. So again, concentrated hydrochloric acid, a source of hydrogen chloride gas, is placed at the other end of the tube. So what do? They close the tube from both ends to stop the gases from escaping. Then after a few minutes, this will come here, this will come here, and the white ring of ammonium chloride is formed. But formed where? Formed closer to the hydrochloric acid end. So from this we can deduce which is the heavier gas. Definitely the heavier gas will travel a shorter distance in the same time as the lighter gas. So it traveled 40 centimeters and this traveled 60 centimeters both at the same time. So definitely this over here is the lighter gas and this over here is the heavier gas. Now, although the gas particles move at a speed of several hundred meters per second at room temperature, yet it takes a few minutes for the white ring to form. Why? This is because the gas particles are in random motion. So they collide with one another and with the walls of the tube. So even though they travel really fast, they're still in random motion. They're still bumping each other, bumping other things. So we see they're in random motion. So they collide with one another and with the walls of the tube. Now, apparently, for this white ring to become visible, it cannot happen by only one reaction or one collision. Actually, many collisions have to happen for this white ring to become visible. The white ring is formed closer to the hydrochloric acid because, as we said, ammonia particles are lighter. They are 17 grams per mole than hydrogen chloride particles, which are 36.5 grams per mole. And as we said previously, if they are lighter, according to the kinetic energy theorem, I think, the lighter they are, the faster they will move. So definitely ammonia moves faster than hydrogen chloride. Now, when the experiment was repeated using concentrated hydrobromic acid instead of hydrochloric acid, the white ring formed even closer to the hydrobromic acid inside. Now we can deduce from this that since it's forming closer to the hydrobromic acid, that the molar mass of hydrobromic acid, which is, I believe, HBr, okay, is greater than, okay, the molar mass of HCl. This is because, of course, hydrogen bromide travels at 81 grams per mole, which is way more than 36.5 grams per mole. So they are definitely heavier than hydrogen chloride particles and travel much slower. Now, diffusion in liquids. Of course, since the kinetic energy of liquids is less than the kinetic energy in gases, the fusion will happen slower in liquids. So the fusion in liquids is much slower than the fusion in gases because liquid particles move much slower than gaseous particles. Okay? So if we're going to go to example 1, and they're going to explain to us what they did. What they did was they added potassium permanganate crystals, so KMnO4, in a beaker of water. So they added, I believe it's supposed to be potassium permanganate over here. Okay, they added it to water. Now what happened is that the water molecules, they collided with the particles of the potassium permanganate, okay? Since the water is colliding with them, they will dissolve in the water. If they dissolve in the water, after that what happens, they will spread out by the movement of water molecules, okay? And they will definitely go from the highest concentration to the lowest concentration. So this is diffusion. So, of course it's gonna take some time, okay? So after a few days the particles have mixed completely with water. Now they state something really important over here. They say diffusion occurs more rapidly if the liquid is hot. Definitely, if you heat a liquid, the kinetic energy will become greater, the particles will move faster, so they're more likely to collide with the other particles and more likely for diffusion to happen. So let's read what they said. This is because the particles in a hot liquid have more kinetic energy than a cold liquid. These particles move more rapidly, thus spreading out more quickly throughout the liquid. Okay, exactly as we said. Then they did example 2. In example 2, they said, when few blue crystals of copper disulfate is put in water. Okay? After a week, the water turns into a blue solution. So this is a case of what? Of diffusion. So these are crystals, they're gonna dissolve into the water, and because they dissolve, they will diffuse as well into the water to give it a color of blue solution. So now they're telling us about measurements. They're telling us in this paragraph that when you're doing chemistry, when you're studying chemistry, you have to do many experiments because you need to be very accurate when you're doing something. So during the study of chemistry, many experiments are carried out and many measurements need to be taken. You have to be really accurate, okay? You have to be correct. It's very important to use the correct apparatus for the required task and to be able to read the apparatus correctly. So some things they measured in this reaction, in this experiment, was time. They measured time. Time you measure it using a stopwatch. Especially, I believe this is a grammar, a spelling mistake. Not especially, it's especially important when measuring reaction rate. So when you're measuring the rate of reaction, you need to use a stopwatch or a stop clock to measure the time. So here the recorded time is, they told us that the smaller clock is for minutes and the bigger clock is for seconds. So reading it, it is approximately 1 minute and here's 1 minute and 22 seconds. Now pay attention, in the exam they might ask you change it to only in seconds, don't put it in minutes, okay? So then put it in minutes. 1 minute is 60 seconds. 60 seconds plus 22 seconds is 82 seconds. So 1 minute and 22 seconds is 82 seconds. Then we go down. So they told us reading. Reading should be to the smallest division only, meaning that you should take it exactly. Don't estimate it to a number that is like, for example, if you have it over here, it is almost, let's say, 26. Don't say it is 28. It's very obvious it's not 28. Like, looking at it, it's not 28. So you have to read it to the smallest division. This includes in temperature, in mass, and in volume. So in temperature, over here, as we said, this is 26 degrees. And over here, this is 20, 21, 22 degrees Celsius. So if I put here over like 25 degrees Celsius, it's wrong. Even though they're 3 degrees different, you have to use the smallest division. And looking at it logically, you'll see that it's not 25. 25 is over here. So it is 22 degrees Celsius. Now, how do you measure the temperature? You measure the temperature using a thermometer, okay? It has intervals of 1 degrees Celsius. Then the mass. How do you measure the mass? You measure the mass using a top pan band. So you put something over here, for example, a block, and then it will measure like this. So something like this, yeah? Now, number 4, we're going to be measuring volumes. To measure the volume of a liquid, you have many ways. You have burette, pipette, measuring cylinder, okay? And the volume of gases is different. So now let's talk about the volumes of liquid. So, when we're talking about liquids, you have 3 ways of measuring the volume. Either a burette, a volumetric pipette, volumetric means specifically for volume, or measuring cylinders, depending on the accuracy. If you need extremely accurate, you use pipettes. If you need like a very accurate, not extremely accurate, you use burettes. And if you just need to mix, you use a measuring cylinder. So a burette is used to measure the variable volumes. Remember, burette, link it to variable volumes of liquids up to 50 centimeter cube. This is what the burette will look like, either like this or like this. And then they'll probably ask you to find the volume. Remember, the volume of a liquid is always in centimeter cubed. Now, we're gonna go down. Pipette. Pipettes are used to measure accurate volumes of liquid. The common capacities are 5, 10, 25, and 50 centimeter cube. So remember, link pipette to accurate volumes. Now, they're telling us you cannot use a pipette to measure the volume of the gas as it is not graduated. It has one calibration mark, meaning it has 1 point over here which tells us like 50 centimeter cubed. So خلاص, only for liquids we use it. because we know in the gas we can compress it, we can make the volume smaller and bigger, whereas in the liquid we cannot. So that's why we are gonna use like only pipettes for the liquid, or like only liquids for the pipette. Okay. Now the final one is measuring cylinder. If you want to use a measuring cylinder, you use it to measure approximate values of liquid. Okay. It can be used to collect and measure the volume of a gas. Oh, so now look. If we go up here, they didn't mention anything about a gas. So that means in the burette and the pipette, you cannot use it to measure a gas. Okay. However, in a measuring cylinder, you can use it to both collect and measure the volume of a gas. But however, to more accurately measure the volume of a gas, you use a gas syringe. Gas syringe looks something like this. So our gas will be over here, for example. Okay, it will fill up all of this space over here. And then just by reading over here, we can know the volume of the gas. Now, just a tiny note they put for us. They told us a gas can also be collected using a gas jar. They said only collected, so you cannot measure it. They told us a gas jar cannot measure the volume of a gas as it is not graduated like a measuring cylinder. So only things that can measure the volumes of a gas are a measuring cylinder and a gas syringe. So now they drew for us what a gas jar looks like. This is how the gas jar is. You have water over here. You have the gas. You have also water. So all of this in the red is water and the gas jar. Then in green, you have the gas. So they put the gas over here. Okay? And over here is the delivery tube to put the gas into the water. So this is how to collect a gas using a gas jar. Now the final thing we can measure when doing a chemistry experiment is the pH. pH means how acidic or basic something is. How do you measure the pH? You use a pH meter or universal indicator. Now, of course, when doing an experiment, you have to be really reliable, because if you do any error, the whole experiment is wrong. They told us data collected during an experiment needs to be repeatable, meaning if another scientist does the same experiment, they will get the same result. And reproducible, same thing as repeatable. Actually, no, they defined what repeatable and reproducible means. Repeatable means the same person does the experiment several times, under the same conditions, and gets similar results every time. Reproducible, on the other hand, means that different people do the experiment under the same conditions and get similar results every time. So now we have three main variables, okay, to make sure that an experiment is repeatable and reproducible. There are three main variables. Controlled variable, which is kept constant or kept the same during the experiment. The independent variable, it is changed during an experiment, and this is always plotted on the x-axis. And then the dependent variable, the variable measured during an experiment. So, for example, let's say we're talking about medication, the effects of medication on an individual. We'll have, for example, one person here and one person here. This person here takes a pill, and this person here takes a pill. This pill does not affect the individual. However, this pill will affect the individual. Let's say it boosts his dopamine levels, okay? So what happens is that he is the controlled variable, okay? Here he will be the independent variable. Actually, the independent variable for him is how much of the volume or the concentration or the amount of medication that will boost his dopamine from taking this medication. So if he takes like 1 gram versus he takes 10 grams, how much will it boost his dopamine? And then, for example, if he takes 1 gram, he will get, for example, 10 times dopamine. I have no idea what I'm saying. I'm just making it up. So if he takes 1 gram, he'll have 10 times dopamine than usual. If he takes 10 grams, then let's say he will have 100 times dopamine than usual. So the dopamine is the dependent variable, or the variable that is measured, okay, during the experiment. Or as you increase this, for example, the dopamine will increase. So the dopamine in this case is the dependent variable. Independent variable is the amount or the mass of medication he's taking, and the controlled variable is, for example, you're going to be using the same person, or you'll use two different people. One person, he takes the same thing but with the same size, to keep it constant. Now, sources of error. Of course, we're all human, we're all gonna do mistakes. So here they told us that every measurement has some degree of error or uncertainty. So we're all humans, yeah? We're all gonna do human errors. So, of course, we're human, so a random error is an unpredictable change in result, like human errors. For example, someone slips, okay? يعني بعيد الشر, someone slips and he has an acid in his hand, he's gonna drop. The volume of the acid decreases, okay? Systematic error. So probably you continue doing the same experiment over and over and you get an error. So at some point you might believe that it's true, this error, but it's probably due to problems with the experimental design, so how much you put, what you did, etc. Or like a defective apparatus, so you used maybe an apparatus that's like wrong, okay? Then, so anomalous, an anomalous error, okay, is something unusual or unexpected. For example, you made the measurement too high or too low as compared to the trend or norm, meaning the normal thing you were supposed to do. Zero error. This is a systematic error, so we go back to here. This is an error from the machine. Okay, for example, an instrument does not read zero when not in use. For example, they gave a good example, balance. You're measuring the mass of something. Okay, it's not reading zero, even when there's nothing on it. So this is a zero error from the balance. So you're not using the balance, but it's giving you zero. Okay, then we have graph plotting. So, of course, to graph the plot, if you remember, we said the independent variable should be on the x-axis. So let's do it like this. X, y. Here we have the independent variable. Here we have the dependent variable. So, dependent is on the y-axis. Make scales as large as possible. Don't do it like me. If you have a full paper, use the full paper. Make it as large as possible to fit everything properly. And they don't need to necessarily start at zero, okay? Label the axis with the variable name and its unit. For example, if you're talking about the independent variable, which is the concentration of medicine, if we are going to use the previous experiment, okay? And then the dependent variable is going to be the level of dopamine. Alright? So to give our graph a title very easily, we're going to title, for example, of this experiment is the change in level of dopamine versus a change in concentration of medicine. Okay? Now, if you're gonna cross the points, they told us, if you're gonna plot the points, they told us use a cross, not a dot. So don't put it like this. No. They told us use a cross like this, for example. And you should use a sharp pencil. So then, they told us draw the line of best fit. Meaning, if I'm gonna draw here, I'm not gonna draw like this. No, this is not the line of best fit. The line of best fit would be something like this. Still, it's not. So it has to cross through every single point. So for example, the line of best fit would look something like this. It may be a straight line, in this case it's not, or a smooth curve. This is a bell curve that we call it. It does not need to pass through all points. In my case, because I drew it small, it does need to pass. But if you're gonna use like a lot of points, for example, one here, but then one here, it doesn't have to pass through all the points. It can miss one. It's okay if it misses one. But it has to be drawn so all the points are evenly scattered on either side of the line. So that is it for graphing the plot. Now safety. Of course, of humans, we're gonna get hurt. For example, remember the person I said, he's holding the acid and he slips. he might hurt himself with the acid. So the safety when planning an experiment is essential to assess risk and identify sources of danger to eliminate them. Now we're talking about elements, compounds, and mixtures. We're going to start with an atom. An atom is the smallest particle of matter, the smallest particle of an element, which shows the properties of that element. Okay? So atoms of the same element have equal number of electrons and protons. So actually it's in all atoms, but what I'm trying to say is that atoms of helium, for example, helium has one electron. So every single atom of helium, pure helium, will have one electron. Okay? What they're saying now is that atoms have equal number of electrons, okay, and equal number of protons, so they are neutral. So, for example, helium has, helium has 2 electrons. That's a mistake from me, because I forgot. Please, I apologize for this mistake. So helium has 2 electrons, okay? That means it will also have 2 protons because it is electrically neutral, same number of electrons and protons. So this is an atom done. Now an element. So we have an element. An element is a pure substance which is made from only one type of atom, okay? It cannot be broken down into simpler substances by chemical processes. So we have an example of an element, neon. For example, you have a bunch of neon. So it is a pure substance, neon, made of only neon atoms, okay? You cannot break it down into simpler substances. If you try breaking it down, you just get neon. So always an element contains the same atoms that have the same atomic number, meaning the same number of protons. For example, oxygen, O2, it has 8 protons. So let's say one oxygen has 8 protons. If we're talking about O2, I think it's also going to be 8 protons. So that means this has 8 protons, this has 8 protons, this has 8 protons, this has, all of them have 8 protons. So, like this, we finished talking about elements. Now we're gonna move on to compounds. A compound is a subject made up of 2 or more elements which are chemically combined together. Meaning you have 2 elements, for example, H2O, you have the elements H and you have the elements O. What do they tell us about compounds? They tell us a compound is completely new material. It will have different properties from its elements. So for example, H2O, water, is a liquid, okay? H2 is a gas. O2 is a gas. So how can a gas and gas combine to form liquid? This has gas properties, this has gas properties, but this has liquid properties. So this just proves that a compound is a completely new material that will have totally different properties from the elements that made it. Now, a compound cannot be separated from by physical means. So, for example, water. If you heat water, if you add heat, this is a physical method, okay? It will not break into H2 and O2. You'll have to do something called electrolysis, I think, or hydrolysis, and you will separate the H2O into H2 and O. Same thing goes for the HCl. Now, we have a mixture. A mixture is a collection of at least 2 or more elements or compounds which are not chemically bonded together. Take orange juice, for example. I don't have red, so let's say this is orange juice, okay? You have the pulp in the orange juice, you might have some seeds. I don't know, you have some stuff in the orange juice, okay? So that means orange juice is not a compound, it is a mixture, since it is made up of at least 2 or more elements or compounds which do not chemically bond together. For example, helium and argon. Helium and argon are both noble gases, meaning they do not react with anything, so they form a mixture, okay? Same thing again, H2 and helium. Even though H2 is not a noble gas, helium is. So the H2 will not mix with helium, so they form a mixture. Now, a mixture can be separated by physical methods. For example, filtration, heating, whatever, you know? So this is a mixture done. Now we came to CQDs. So CQD number 1, define an element, a compound, and a mixture. An element is a substance that cannot be split into simpler substances by chemical methods. So what does this mean? An element is a substance. If you break it down, you cannot break it down even more. Like, it is the most basic substance, okay? Basically saying that you cannot split it into simpler substances anymore. It is in its simplest form. Now, a compound, however, is a substance made of two or more elements. Substance made of two or more elements that are chemically combined together, okay? And you can separate them. You can separate, I don't know if I wrote it correctly. You can separate them by chemical means because they are bonded together chemically. Now, a mixture, however, is a group of two or more substances that can be separated by physical means, meaning they are not bonded together chemically. So we say they are not chemically bonded together. That's CQD 1 finished. Now CQD number 2. We need to classify the following as elements, compounds, or mixtures. Blood is very easily a mixture because you have plasma, white blood cells, red blood cells, platelets, everything in blood. So it's a mixture. You can separate them even. Oxygen, however, is an element. Ammonia, which is NH3, is a compound. So you cannot separate it by physical means, but you can separate it by chemical means. Finally, orange juice is a mixture. Now we have some words to remember. We have solvent is a substance that dissolves a solute. For example, water is the universal solvent. Solute is a substance that dissolves in solvent. For example, salt. You have salt will dissolve in the water. You have a solution, which is solute dissolved in solvent. We call this a solution. It's a homogeneous mixture. Homogeneous means you see it as one thing, okay? Homogeneous, I'll just write it a note. One thing. Even though they're not one thing, you see it as one thing, which is a mixture of more solutes, one or more solutes dissolved in a solvent. Saturated solution is when you add so much solute that it does not dissolve anymore. So a solution containing the maximum concentration of a solute dissolved in the solvent at a specified temperature. Residue is the solid or the substance that remains after doing a physical process such as evaporation, distillation, filtration, or any physical process such as melting, freezing, etc. We call this residue. Now, filtrate, on the other hand, when you're doing filtration, okay, you're going to have residue at the top, which is the solid, and then the filtrate is the liquid or the solution that passes through the filter paper. So it will go through the filter. So we have some separation techniques. They include the separation techniques chosen depends on the type of substance that needs separating. Okay, to know which substance we will use which separation technique, we need to look for the differences. Okay, look for differences in the properties of the components and their mixture, such as their state, solubility, melting, boiling point, and so on. Then after that, pick the best advantages, the best takes. Pick the method that best takes advantage of this difference. For example, we have filtration, we have suitable solvent, we have crystallization. I think these are, no. Then we have a separating funnel, simple distillation, fractional distillation, chromatography. We have then the RF value. Then it's like the purity of solids and etc. So let's start over here by filtration. Okay, so remember, anytime you see an insoluble solid, okay, with a liquid, any solvent liquid, then you will use filtration. So very simply, how we're gonna do this is we're gonna take the mixture, we're gonna pour it into the filter paper. Okay, let me explain it from here. We have the solution over here. Let's say this is the cup, and then this over here is our solution. Okay, with these stuff over here that we need to separate. So what did they do? They put the solution in here. we have a filter paper, okay? The filter paper is inside over here. They placed it in the filter funnel, and then they placed the mixture inside. So what happens is that the liquid or the solution will pass through the filter paper and it will go as filtrate. Of course, it will be collected in a conical flask that I cannot trace, okay? And what remains on top is the residue. So then, they told us that the residue is washed with a little more solvent, the residue is dried by spreading it out on the filter paper and either allowing the liquid to evaporate on its own or placing a paper in an oven. So that was for filtration. Now we move on to suitable solvent. This method can be used to separate a solid mixture if a solvent can be found that dissolves only one of the components. So let's say, for example, we have a cup, a very famous example, okay? And we have salt, that we will put it blue, bunch of salt, okay? And then in pink, we're gonna have sugar. How do we separate the salt and sugar, okay? We cannot taste because they're all mixed up together, okay? So they look the same, so it's gonna be very hard to separate, and they're very small grains. So what are we gonna use? We're gonna use something called suitable solvent. Why? Because salt and sugar both dissolve in water, but sugar, on the other hand, dissolves in alcohol, whereas salt does not. So what did they do? They said, we're gonna use separation of salt and sugar. Find a suitable solvent. For example, sugar dissolves in alcohol, whereas salt does not. Then we're gonna dissolve the mixture in the minimum volume of alcohol, so all the sugar will dissolve. After that, we're gonna filter the salt, and so now as our residue, we're gonna have salt, and our filtrate will be the sugar alcohol solution. Then we're gonna wash it with some alcohol and leave it to dry. Now the filtrate, which is the sugar alcohol solution, we're gonna gently heat it over a water bath. Why we didn't use a Bunsen burner? Because alcohol is flammable, okay? So that's why we used only a water bath heated by an electric burner till the liquid evaporates. So after this, we have a process called crystallization. What do we do in crystallization? Crystallization is a method in where we are going to separate a solid from a solution in which it is dissolved. For example, we're going to take salt and water. Let's say the salt dissolved in the water, okay? They told us the method to separate the salt and water is through crystallization, okay? Now, the disadvantage of crystallization is that you're gonna lose the solute. You're gonna lose the solvent, in this case, which is water. Water solvent, you are gonna lose it. So they told us the process. You're gonna heat the solution in an evaporating dish directly over a flame till most of the liquid evaporates, okay? So you heat in an evaporating dish till most of the liquid evaporates. After that, you put it in a steam bath and then you gently heat till the crystallization point is reached. What's the crystallization or the saturation point? Or how do you check it? It is checked by dipping a cold glass rod in the solution from time to time and checking for crystals formation. Crystallization or saturation point is the point at which the crystallization starts or crystals form. After leaving it in a steam bath, you're gonna leave it to cool, okay? After that, you're gonna filter the crystals out. You're gonna then dry the crystals between two filter paper without pressing it or in open air. Why without pressing it? Because if you press it, you're gonna crush it. Also, this method is used to make the small pieces of salt, the small crystals of salt, into one big piece. So imagine after crystallization, it will turn out something like this. So that's crystallization explained. So now we have 3, 5, and 6. Briefly describe how to separate a mixture of salt and sand into its constituents. Very simply, first thing we're gonna do is we're gonna see we have salt and we have sand. Let's take it like this. We have the pink is salt and the blue is sand. It's gonna take a really long time to separate them, okay? So very simply, we're gonna use something called selective solubility. So by using selective solubility, we're gonna put water, okay? And then the salt dissolves in water, whereas the sand does not dissolve. So now we're gonna end up with what? We're gonna end up with a salt water solution and sand. So this is salt water solution plus sand. So the salt dissolved in the water, whereas the sand did not dissolve. The very next step we're gonna do, okay, after obtaining the salt water solution is we're gonna do filtration. When doing filtration, we're gonna get a filtrate, which is what? Filtrate, which is the salt water solution. And then our residue from filtration is gonna be the sand. So right now, we already separated the sand from the salt water solution. After filtration, we are left with a filtrate of the salt water solution, but as we need only salt, so how do we obtain only salt? We are gonna use crystallization, and by using crystallization, you will obtain the salt crystals. So this is how you will separate a mixture of salt and sand into its constituents. Now CQD number 5. Give the name of an apparatus or the name of a technique you can use to separate the following mixture. A mixture of sulfur and steel. Very simply, steel is attracted by a magnet, but sulfur is not attracted by a magnet. So you're going to use a magnet to attract the steel. Then, the second thing we're going to do is a mixture of cooking oil and water. We know that oil and water do not mix together. So whenever we have two liquids that do not mix together, let me write it by number, two liquids that are immiscible, meaning they do not mix together, okay, you are going to be using a separating funnel, okay, or something called decantation. I don't know how to say it. Decantation. Decantation basically means using a separating funnel. So instead of saying this long hard word that I can't say, or if you can say it and use it. I can't say it personally, so what I will write is that two liquids that are immiscible, do not mix with each other, I will use a separating funnel. So that's CQD number 5 done. Now we have CQD number 6. They're telling us name the most suitable technique used to obtain large potassium nitrate crystals from its aqueous solution. Then they want us to describe how this technique is. They need crystals. Anytime they need crystals, it is crystallization. I apologize if my spelling is bad, okay, because my spelling is not the best. So I believe there's another L or something like this. So it is crystallization. Now to conduct this technique, the very first thing we're gonna do is we're gonna heat the solution, okay, until most of the solvent evaporates. This is step evaporates. This is step number 1. Step number 2, you're gonna transfer the dish to an evaporating dish, okay? So heat in evaporating dish, okay? But we heat it using a water bath, because if you're using, for example, alcohol can be flammable, so that's why they say use a water bath. After heating it in a water bath, we're gonna leave it to dry overnight. So personally, how I would remember something like this is first heat till most of solvent evaporates, then heat in evaporating dish, and then leave to dry overnight. So just keywords. First step, heat until most solvent evaporates. Heat in evaporating dish, water bath, leave it to dry overnight. That's CQD number 6, done. Now we move on to the separating funnel. So very quickly, a separating funnel is used to separate two immiscible liquids that do not mix in each other. So they told us a separating funnel is a glass funnel with a tap at the bottom. So basically what they're gonna do is they're gonna put the liquid mixture inside, okay, the separating funnel. Then usually the liquid with the, that is less dense will go up, the one more dense will go down. So in this case, if this is 1 and this is 2, 1 is less dense than 2, and 2 is more dense than 1. So then when you open this, the liquid with the higher density will go down, okay? And then you're gonna wait a while until you see that the liquid with the higher density is almost finished, then you close it, okay? After that, you use a different cup or a different cylinder to take the other liquid, and then the two liquids are separated. That's it. Now we have simple distillation. Now, simple distillation is a method used to separate a pure liquid from a solid, or sorry, not necessarily a solid. It's more a pure liquid from a solution. So, for example, if we're gonna say a solid, okay, like I said, you're gonna separate pure water from an aqueous solution of sodium chloride, which is NaCl, which is table salt. So what they are gonna do? First thing is the solution is heated until the liquid with the lowest boiling point, most volatile boils. So if we're taking the NaCl pure water thing, okay, definitely the liquid has a lower boiling point than salt, so it will evaporate first. So after that, the water vapor will travel, okay, it will enter the condenser. Now in the condenser, you have the cold water goes from the bottom. So follow the arrows. The cold water goes from the bottom, and then the cold water will go out from the top. So it goes in from the bottom and out from the top. After this cold water will cool down the water vapor, so it will condense and become pure water. Now, the collected water is called distillate, or the collected liquid, okay? And then the liquid left, or for example, in this case, the salt, is gonna be called residue. So if we're gonna like summarize distillation, it's two processes: evaporation, condensation. First, you're evaporating the liquid with a lower boiling point, then you will condense it to form the pure liquid. So now they're asking us, which of the following mixtures are best separated by simple distillation? Sodium bromide and aqueous solution, for sure, because you will separate the sodium bromide, which is an AbR, which is also a salt, from the aqueous solution. Sand, salt, and water, definitely not. If you're gonna do simple distillation, you're gonna have sand and salt, which is still not separated. Water, alcohol, solution, no. Why do we not use it? Because we're using a flame, and alcohol is flammable. So to separate water and alcohol, we're gonna use another process. And anyways, water and alcohol have really close boiling points. So we're not gonna use this process for water and alcohol. Sugar and water solution, for sure we're gonna use it. Then any mixture of miscible, meaning they mix with each other. Liquids having close boiling points, definitely not. So the only two answers are A and D. So now we're gonna go to fractional distillation. This is a way to separate what? To separate water and alcohol, or any mixture of miscible liquids having two close boiling points. So if we go down, they say the same thing over here, which is this method is used to separate two or more miscible liquids with close boiling points. Example, the separation of ethanol during fermentation. Now, fermentation is the production of ethanol. It happens when yeast will break down sugars, okay? So what happens is that we get ethanol, okay, and carbon dioxide from this process, but of course there's gonna be water. So to separate the water and the ethanol or alcohol, we're gonna be doing fractional distillation. They told us, first thing, the solution is heated until the component with the lowest boiling point, in this case, which is alcohol, will evaporate. After that, they will travel up and enter the condenser. Why did they say that the vapors and not the vapor? Because they have close boiling points, they will both evaporate. But the one with the lower boiling point will evaporate fully, whereas the other one will partially evaporate, okay? After that, they're telling us once all of the most volatile component is collected, the next lowest boiling point component starts to boil, and its vapors enter the fractionating column, condense back, blah, blah, blah. So basically what they did, they heated. Since they have close boiling points, one will go up, okay, and the other of the, like a little part of the other one will join it. So what happens is that with these, the crystals, or like the glass beads, they will cool down the one that did not reach its boiling point yet. So if we're talking about ethanol and water, let's say we put it at 90 degrees. 90 degrees is not the boiling point of water, but it's way higher than the boiling point of ethanol. So definitely ethanol would have been totally evaporated. So the little part of water that got evaporated, okay, will be condensed from the glass beads and will return back to the bottom. Whereas the ethanol cannot be condensed anymore, so it will go through the condenser and form a distillate of ethanol. So they told us it's not like able to separate them 100%, sure, but you will have a higher percentage, okay? In the collected distillate, you will have a higher composition of the more volatile component. So yes, يعني, in this one over here, you will have ethanol and water, but you will have a higher concentration of ethanol because it's the distillate. So part E, which of the following mixtures is best separated by a fractional distillation? Fractional distillation, definitely we need ethanol, water solution. They have to be able to mix into each other and close boiling points. Oil and water do not mix in each other. Salt and water do not have close boiling points. Sugar and alcohol do not have close boiling points, but definitely we use fractional distillation on any mixture of miscible liquids having close boiling points. So that's CQD 8 done. Now we reached chromatography. Chromatography is really nice, and I believe there is an equation for chromatography. So very simply, chromatography is used to separate soluble colored stuff like ink, food coloring, clothes that are stained or something like this. I don't know. Anything with dye, with a dye or a pigment. So they told us that there are many different kinds of chromatography, but they all depend on the same principles, blah blah blah. The mixture is dissolved in a fluid and allowed to pass through a second material. Okay, so first thing for chromatography, they dissolve the mixture in a fluid. They call this the mobile phase or solvent. Okay, after this, they pass it through a second material called the stationary phase. Now they're telling us paper chromatography is a method used to separate mixtures of soluble colored substances using a suitable solvent. So example, chlorophyll, which has green pigment, ink, which has lots of colors, and food coloring. Okay? Soluble colorless substances using a suitable solvent and a locating agent. Example, amino acids, from a mixture of amino acids. So very simply, you can use it for stuff with color, and you can use it for stuff without color. Okay? So an example they gave us is the separation of black ink into its components. They told us, summary, you're gonna put your solution, okay, which is black ink in this case, you're gonna put it on a concentrated paper, on a paper with a concentrated dot, and you call this the stationary phase. You draw a line, which is the baseline, you draw it in pencil, not in pen, because pen contains colored pigments. After this, you're gonna put it in a suitable solvent, which is called the mobile phase. After this, you should put the level of solvent below the baseline that you drew in pencil, okay? Then, after a while, using capillary action, the solvent will start rising. As it rises, okay, the components or the dyes are separated. So it will, the filter paper in this case will suck up the, the solvent, and then the solvent will separate the ink. After that, you're gonna wait until the solvent is about 1 centimeter from the top, so the paper has to be totally immersed. And then you draw another line in pencil to show where the solvent reached. Then this line is called the solvent front. And then here they're just telling us that different components have different distance travel based on their solubility. Okay. The most soluble component will travel the farthest distance, and the least soluble component will travel the shortest distance. And then you would have finished, and the paper with the separated components is called a chromatogram. So that's basically it. Now we reach CQD number 4. What process can be used to separate the dyes in food coloring? Very simply, actually it's not it's chromatography. Okay? So then here he told us, or like they're telling us, sometimes the components of a mixture are colorless. Example, amino acids mixture, nothing will be visible on the chromatogram. In that case, the chromatogram can be sprayed by a suitable locating agent. Locating agent will give color to the amino acids. So yeah, just as I said, it will color them. Now here we reached an equation which is called the RF value. RF value, or retention factor, is the distance traveled by a component divided by the distance traveled by the solvent. So for example, if you're talking about ink and you have component color red, you're gonna see the distance traveled by the component color red, so distance red, over the distance of the solvent. Just an example, okay? So the retention factor, or RF, is a physical property. Different substances have different RF values, so that's what makes it possible to identify a substance. In addition to separating and identifying substances in a solution, chromatography can also be used to check the purity of a given substance. So now to understand further how we're able to check the purity, we're gonna see interpreting chromatograms, okay? So now we're gonna interpret chromatograms. Consider the following chromatogram of 6 substances. Substances 1 and 2 and 4 are soluble, pure substances because the initial spot moved up the paper with the solvent did not split. So look, if you're gonna go 1, you're gonna go up, you will see that it only passes through this over here. If you're gonna go through 2, you're gonna see it passes through only this over here. If you're gonna go through 4, you will see it passes through only this over here. But if you were to go through 3, it would pass through 2 substances. Through 5, it passes also in 2 substances, and 6 also in 2 substances. So that means they are pure substances. 3, 5, and 6 are mixtures because they moved with the solvent and split into more than one spot. Then dyes 2 and 5, 3 and 5, and 3 and 6 have a common component. So 2 and 5 meet here, 3 and 5 meet here, and then 3 and 6 meet there. They have a common component, the same RF value. And then they told us if a substance does not move up and remains on the baseline, it's considered to be insoluble in the solvent, so it does not dissolve in the solvent. So now CQD number 9 grid. So they're telling us the following shows a chromatogram of a dye that was separated into 2 components, A and B, using paper chromatography in a solvent X. If we're to go down, we will see in part A they're asking which of the 2 components of the dye is more soluble in solvent X and has a least affinity to the paper. We know always the more soluble something is, the farther the distance it will travel. So which traveled the farthest distance is A. So A is definitely, or component A, because they asked which of the 2 components, A is definitely the dye that is more soluble in solvent X. So then if we go down, they're asking us, to find the RF value for component A. Very simply, to find the RF value of component A, we're gonna see the distance traveled by component A, which is 8 centimeters, divided by the distance traveled by the solvent, which is 12 centimeters. So the RF value is 8 over 12. So that was it for this one. Now we have CQD number 10 grid. A mixture of amino acids is a colorless solution and can be separated using chromatography. Describe how the chromatography procedure should be adapted to reveal the amino acid spots on the chromatogram. The chromatogram. Sorry, I'm not able to pronounce it. The chromatogram. Very simply, they told us whenever we have amino acids and we want to show the color of the amino acids, we should use a locating agent. So very simply, just use a locating agent. So now they're So now they're telling us the purity of solids and liquids. To check if a solid or liquid is pure, we have to determine its melting point and boiling point. Very simply, check for the solid its melting point. Then For example, NaCl. And so the melting point of NaCl is 801 degrees Celsius. So what you're gonna do to check if it's pure NaCl is you're gonna make it go to 801 degrees Celsius. If it melts, then it's pure NaCl. If it melts before 801 degrees, it's not pure. If it melts after, it's not pure. It has to melt at exactly 801 degrees Celsius. By melt, I mean like fully melt. It will change fully into a liquid. Same thing goes for liquids, for the boiling point. For example, water. The boiling point of water is 100 degrees Celsius. If you want to check if this water is pure, boil it. Does it boil at 100 degrees Celsius? If it does, it's pure. If it doesn't, then it's not pure. So pure substances have sharp, fixed melting and boiling points. Impure substances, okay, pay attention. Impure solid will have a lower melting point than the pure solid, as impurities decrease the melting point, and an impure liquid will have a higher boiling point than the pure liquid, as impurities increase the boiling point. Now if we're gonna go down and see some examples. They told us pure water boils at 100 degrees Celsius, while salt water with NaCl boils at 102 degrees Celsius. Pure ice melts at 0 degrees Celsius, while ice that has salt in it melts at about -4 degrees Celsius. So again, chromatography can be used to determine the purity for colored dyes, as we discussed earlier. Now, so we are given a sample of colorless liquid in a test tube, and we are told that this is water. Okay, how can we assess that this is pure water? Very simple, by checking its freezing point and its boiling point. If it freezes at exactly 0 degrees Celsius, then it's pure water. If it boils at exactly 100 degrees Celsius, then it's pure water. Now, methods of purification. Example, to separate salt from rock salt. Dissolve the solid in a solvent in which it is soluble. After that, we're going to filter the mixture to remove any insoluble substances, which are impurities. After that, we're going to evaporate the solution to reduce its volume and then leave the solution to crystallize. After that, we're going to filter the crystals and whatever. Basically, what they did, they made, for example, if we're going to separate salt from rock salt, we're going to put it in water. The salt will dissolve. After that, we're going to filter the mixture, and the impurities will not dissolve, they will remain as a residue. After that, we're going to evaporate the solution to leave the solution to crystallize, okay? After that, the crystals, we will leave them to dry, and then we will get a pure solid. Now, to purify impure liquids, you have two methods, either simple distillation or fractional distillation. Now here we're going to be working with gases. So we have 4 methods of collecting gases. You can use the gas syringe to collect any gas. You can use upward delivery to collect gases that are less dense than air. You can use downward delivery to collect the gases that are denser than air. And then finally, you can use the method where gases are collected over water if and only if the gas is insoluble in water. So let's go down. We're going to have drying of gases. We have not too much. We just have the drying of gases. Very simply, to dry the gas, we're going to pass it through a drying agent. They can be either solids or liquids. So for example, you can use anhydrous calcium chloride solid to dry the gas, or this is a solid drying agent, or a liquid drying agent is concentrated sulfuric acid. So now we have some notes. We have toxic poisonous gases like chlorine, or pollutant gases like nitrogen dioxide should be prepared in a fume cupboard as a precautionary measure. So they're very dangerous to us. We have to prepare them in caution. Concentrated sulfuric acid is never used to dry ammonia because ammonia is basic, sulfuric acid is acidic, so they will do a neutralization reaction. They might cause an explosion, they might make water, so you won't be really drying the gas. And then the most suitable drying agent for ammonia gas is calcium oxide solid. So now, number 12. Okay, so we need to calculate the molecular masses of H2S and NH3. The molar mass of H2S is 34, and then the molar mass of ammonia is then 17. So as a simple fraction, we can put it either as H2S over NH3 or NH3 over H2S. So let's say I'm going to do NH3 over H2S. So it's going to be 17 over 34, which is 1 over 2. So we know that H2S is definitely way denser than NH3, or it has double the density of NH3. Now, which of the two above gases is collected by upward delivery and downward delivery? Upward delivery is for the less dense, and downward delivery is for the more dense. But of course, less dense than what? Less dense than air. So air, memorize that its molar mass is 28.8. Okay, we know H2S is 34 and H3 is 17. So definitely 34 is heavier than 28.8, so it's more dense. So we're going to use H2S, we're going to use downward delivery. 17 is less than 28.8, so we're going to use upward delivery for NH3. So now they're asking us in CQD number 13, name two common drying agents that are used to dry gases. You have the anhydrous calcium chloride. I will write it. Anhydrous, I believe you spell it like this. Calcium chloride. And then this is D. And then you have concentrated sulfuric acid. Sulfuric acid. So this is CQD number 14. Number 13 done. Now we reached CQD number 14. Three gases that are highly soluble in water are ammonia, NH3, sulfur dioxide, SO2, and hydrochloric acid, HCl. Me, myself, I didn't know, so I had to search them up. For now, memorize these three. So NH3, SO2, and HCl. If you want to search it up, search three gases that are highly soluble in water. Now they want us to draw a labeled diagram of a setup we can use to make an aqueous solution of a highly soluble gas. So very simply, we can use a test tube. Okay, we're gonna have a stopper over here. Then we're gonna have a tube over here, and this tube the gas will enter. Then we'll have another tube over here. From this tube the gas will exit. And then here we have water. So let me redraw it, okay, because my drawing skills are not the best. Give me a minute so I can draw it properly. Okay, so this is our tube. On the tube we have a stopper. Then we have a smaller tube that is entering. This is from where the gas will enter. Okay, and then it will enter our liquid. Then we have like an even smaller tube over here. Sorry for the horrible drawing because I can't draw. So we have like this over here for the gas to enter and then for the gas to exit. Okay, you can do this or like have a beaker or something like a beaker and put an inverted funnel. And that's how you can make an aqueous solution of a highly soluble gas in water. Now CQD number 15. They told us the following diagram shows a chromatogram for a mixture of two amino acids R and T. Now they want us to find the identities of the amino acids prepared. So to find out the identities, very simply, we have R and T. T has a distance of what? Of 6.16 minus 1. Why? Because we're going to take the distance from the baseline. So this distance over here becomes 5.16. Then R has a distance of 8.2 minus 1 because we're going to take into consideration the baseline. So it's going to be 7.2. Then we're going to divide it by the distance traveled by the solvent front, which is 13 minus 1 because that's our baseline, so 12. Now let's find the RF of R. It's going to be 7.2 over 12, which is 0.6. Then the RF of T, it is 5.16 over 12, which is 0.43. So remember 0.43 and 0.6. Let's go up. What has an RF of 0.43? We have proline. What has an RF of 0.6? We have valine. So our answer is proline and valine, so it is D. Now we proceed to CQD number 16, top. So now let us answer CQD number 16. The apparatus shown below is used to collect gases in the lab. Name apparatus A. Apparatus A is, I believe, a separating funnel. Separating funnel. So A is separating funnel. B is a tube to deliver. Okay, and C is, I think it's a measuring cylinder. So C is a measuring cylinder. So that's part A done. Part B, a student used this apparatus to collect sulfur dioxide gas. Explain why the student makes a mistake using this apparatus to collect sulfur dioxide gas. I believe since sulfur dioxide is denser than air, okay, it's gonna escape from the bottom, so from here. So since sulfur dioxide is denser than air, it will escape from the measuring cylinder over here. Now, name one gas that can be collected, any gas that's less dense than air. So for example, hydrogen gas is less dense than air. Now they're telling us, suggest a modification on the apparatus to collect sulfur dioxide. You may include a diagram. Very simply, just flip the measuring cylinder. Flip the cylinder. If you flip the cylinder, then the gas will be collected from the bottom. So that's CQD number 16 done. Now finally, we reach CQD number 17. Okay. A student investigated the rate of reaction between dilute hydrochloric acid and excess calcium carbonate. The student used a gas syringe to collect and measure the amount of gas released as shown in the diagram, okay? They told us in part A, use the syringe diagram to record the volume of carbon dioxide gas released. Okay, so let's answer these. Here the total syringe collected is, the total gas collected in the syringe is 0, since there's nothing collected. Here is 30, here is 45, no it's not 45, it's 46 centimeter cube. Then here it is 59 I think, okay. Then over here is 65, over here is then 70, and then we have 70 again, and then over here again it is 70. So now we need to plot them. So very simply, let me just remember the time quickly. We have 0, 30, 60, 90, 120, 150, 180, 210. Okay, so at the time of 0 seconds we collected 0 gas. At the time of 30 seconds we collected 30 centimeter cubed of gas, so it's going to be here. At the time of 60 seconds we collected around 46, so I believe it's going to be here. At the time of 90 seconds we collected 58, so it's here. At the time of 120 seconds we collected 65, so I think it's here. Then at the time of 150 seconds we collected 70. Here. 180 we collected 70. Then 210 we also collected 70. So if we're going to connect our graph, it's going to look something like this. Now let's go down. They said use the graph and deduce the volume of hydrogen gas released after 80 seconds. So I think the graph was 1 second, let me return the graph. So our graph looks something like this. So they need us to collect the volume collected at 80 seconds. So let's go at 80 seconds. So I'm going to say is here. We collected an approximate volume of, I'm going to say 55 centimeter cubed. So at the time of 80 seconds, we collected 55 centimeter cubed. Now, D. if instead of a gas syringe, another student collected the gas using an inverted 50 centimeter cubed measuring cylinder filled with water. They said suggest an error in this experiment because it's not going to be sufficient. We have maximum 70 centimeter cubed, and here he gave us 50 centimeter cubed only, so we're going to say inaccurate measurements. They told us suggest an improvement to fix the error other than using a gas syringe. Very simply, increase volume of measuring cylinder. That's part D finished. Now finally we reach the last questions. So E, part I, calculate the volume of hydrogen gas collected between 30 seconds and 120 seconds. Between 30 and 120 seconds. Actually, it's very simple. They told us, okay, very simply, to calculate the volume of hydrogen gas collected between 30 seconds and 120 seconds, okay, first of all, we're going to find the average rate of reaction. To find the average rate of reaction, I'll let you guys do it. You're going to do the volume of the gas collected divided by the time. So, if we're going to go up, we're going to see, for example, at 30 seconds, we collected a volume of 30. So, okay, I'm going to cut that part out. Okay. Part E. The following expression is used to calculate the average rate of reaction. To calculate the volume of hydrogen gas collected between 30 seconds and 120 seconds. Very simply, without going to the graph, we're just going to go back up here. If you remember, at 30 seconds, I think the volume collected was 30, and at 120 seconds, the volume collected was 65. So now if we're going to go down again, we're going to do that. The volume of hydrogen collected between 30 seconds and 120 seconds is time final, time initial. We're going to do time final minus time initial. Okay? So it's 120 minus 30, which is 90. So this is our time in seconds. But the volume of the gas collected is volume final minus volume initial. Our volume final of 120 was 65 minus volume initial, which was 30. So the volume of hydrogen gas collected between 30 seconds and 120 seconds is 35 centimeter cubed. Okay, now that we have the time and we have the volume, we can find the average rate of reaction, which is what they will ask us here. Okay, so it's gonna be 35, the volume, divided by the time, 90. So it's gonna be 0.388, rounded 0.39. So now we finished from question E. Question F, they asked us to sketch, so I'm not gonna sketch, I'm just gonna explain. Sketch on the same graph the expected curve if the concentration of hydrochloric acid was increased. I believe hydrochloric acid is the limiting reagent, but let's double check. Okay, here they tell us between dilute hydrochloric acid and excess calcium carbonate. So that means the hydrochloric acid is the limiting reactant. So if we are going to increase the concentration of the limiting reactant, then definitely both the slope and the plateau are going to be affected. So the curve is going to be above the original curve. And the final volume of hydrogen is also increased. So I'm like too tired to go back up. So if this was our curve originally, then after increasing the concentration, it would look like this. Okay, so now they're asking us a question. If the gas collected was hydrogen rather than carbon dioxide, would it have been possible to collect it over water using a 250 centimeter cubed measuring cylinder? One thing you should know is that carbon dioxide is dissolvable, or it dissolves in water, as hydrogen is insoluble in water. So definitely collecting it over water, we're talking about hydrogen gas, using a 250 centimeter cube measuring cylinder would work definitely, because it is insoluble in water, unlike the carbon dioxide. So thank you guys for watching. I really apologize for the long video, and I hope you guys enjoyed. Have a great day.